let me talk about Helmholtz free energy. And this is a very physically important object, and it's very useful when T, the temperature, is constant. Okay, and this is the case for the canonical ensemble. So, total energy is conserved, right? So total energy, E, or which we also call internal energy, U, E or U, is conserved, right? Because energy is conserved. But we know from real life experience that, useful energy is reduced over time, right? The amount of useful energy is reduced over time. And that is a consequence of the second law. So the second law of thermodynamics tells us that over time, the entropy increases. At best, it remains the same, but it increases. And what entropy does is that it makes energy, the more entropy we have in a system, the less useful energy we have in that system. So entropy gives us a measure of the unusable system, so to speak. So, if I give you entropy, you can make something which has a dimension of energy by multiplying it with temperature, right? So free energy is the energy that you can still use. You still have access to. It's the total energy which is conserved minus T of S, T times S. And because, in a system, S increases over time in a closed system, that means that the amount of free energy decreases over time. Okay, so that's basically what the free energy is useful. And so if I take the small variation of the free energy, then, if I have dE minus S dt minus T of ds, now the first law tells us that dE is T of ds minus P dV, and then we have S dt minus T of ds. And then these terms cancel out, and then we have d of f is minus S dt minus P dV, where so this means that f is a function of temperature and volume, and P is minus f by, minus derivative of f with respect to v, and of course keeping T constant, and S is minus the derivative of f with respect to T, keeping the volume constant. Okay, so this is the free energy, and because it's got dt in it, so we see that if we keep the temperature constant, free energy is related to the work that is done by the gas.
Sir, I had a confusion.
Yes, please.
So when we have any sort of uh, things like this, free energy, or let's say other things, state variables, so like we take the differential and we end up with like in this case like it's dt and dv. So when we do it in this way, like we have dt and dv, then why is it always that we end up concluding that we can completely describe this f in terms of t and v?
So because it's a Legendre transformation. This is a Legendre transformation, and we saw in a tutorial that Legendre transformations are transformation in which you don't lose any information. It's a completely reversible transformation, right?
Oh,
So we are doing a Legendre transformation, where remember E, the internal energy was a function of S and V, right? And what we're doing is that we are handing in S, and we are taking T instead. So we end up with a function which is no longer a function of S but a function of T. Right? This is basically how we do what we do in Legendre transformations. Did you do the tutorial on Legendre transformation, Mahi?
No, sir.
Okay, so it's somewhere on Slack. I would strongly recommend that you go and do that. And also there was I think there were some questions on this in one of the, after the tutorial, somebody asked a question in a class. So there is some, there is a short video on it as well, okay, explaining what happened. So the Legendre transformation is this really beautiful transformation where you change the functional dependence to a new variable, but you don't lose any information. Okay. All right. So, any more questions? Okay. So, so we have defined the free energy, and now let's discuss, these statements I made above in the context of a specific example that you are familiar with. Okay. So let's take the example of the two-level system. So we have a bunch of particles, and well, a very large number of particles, which have two energy levels, right? So this is something you did in the tutorial, and also we did it in class. So remember that if I look at the entropy of this thing as a function of the fraction of states which are the fraction of the system which are occupied, so basically the total energy, we saw that this was the entropy, right? So the entropy had a maximum and then it went down. And this was kind of the physical region because this was the region of positive temperature, whereas this was the region of negative temperature, and we were not interested in that. So now the thing is that we also looked at the heat capacity of the system, and we found that the heat capacity had what was known as the Schottky anomaly. And the Schottky anomaly is this bump. But what's interesting is that as the temperature, is increased, you'd think that, okay, when the temperature is very high, there's a lot of energy in the system. The temperature, when you are increasing the temperature, you are giving the system a lot of heat energy. So a lot of the particles should flip and get to the highest level, right? The system should increase in its energy. But we saw that, the heat capacity is actually going down, right? So the ability of the system to absorb energy is actually reduced the higher the temperature, right? And the explanation of this is in this diagram. And what's happening is that as temperature is increased, we are in this region, right? So our entropy is increasing. And what is happening is that although there are plenty of available states, it's just that as we go to a higher and higher temperature, the absorption of energy is dominated by the fact that there are more and more states in which that energy can be absorbed in, and therefore the entropy is increasing. So even though we have lots of empty states where that energy can be absorbed and it can flip to a higher energy state, but because the entropy is increasing, that transfer of energy is not happening very efficiently. So this is an example of the fact that how increase in entropy stops us from, from transferring energy into the system or increase the internal energy of a system in an efficient way. Okay? Any questions? So free energy is perhaps is the quantity that is most directly related to the partition function. So free energy is actually, and you can work this out, is if you take the partition function and you write it as an exponential, then the exponent up to the factor of kBt is exactly the free energy. Okay, so free energy is minus kBt log of Z.